Hey guys, and welcome back to a new video. In this video, I will show you how you can encrypt data stores.
supported languages, Java, JavaScript, and C++ as well. And if you're completely new to data structures and algorithms, I definitely recommend checking out some of the courses I have available for pro members. There's a 25% off launch sale going on right now. You can get a lifetime access plan, which will give you access to all current and future courses. Pretty soon I plan on doing system design and a lot of other things as well, like full stack web development and a lot more. Okay, without further ado, let's get started now. Hey everyone, welcome back, and let's write some more neat code today. So today let's solve climbing stairs. So this is going to be another dynamic programming problem, and this is definitely more on the easy side, definitely compared to some of the really hard dynamic programming problems that we've been solving recently. But I still think that this is a good problem to really understand the fundamentals, understand, the brute force, and taking that brute force, using memoization, and then of course getting the true dynamic programming solution. And by the way, if you don't already know, we have been tracking making a list of blind 75 questions on this spreadsheet. So today we're going to be solving this dynamic programming one, the climbing stairs problem. So I will be adding the solution once this video is uploaded. And the link will be in the description if you do want to take a look at this sheet. So the problem statement is pretty simple. We're climbing a staircase and it's going to take us n steps to reach the top of the staircase. Every time we take a step, we have two choices of how we can take a step. We can either just take one single step, or we can take two steps at once. And all we want to know is how many different ways can we get to the top of the staircase. So let's look at the first example, n equals 2. That means we need to climb 2 steps. So we could draw the picture kind of like this, right? So let's say we start over here, right? This is step 0, basically, when we haven't climbed anything. And our goal is to get up here, which clearly is 2 steps, right? So starting from here, we know we can make two choices, right? We can take 1 step and that would land us over here, or we could take 2 steps and that would land us over here. So already we're seeing one way is to just take 2 steps, right? That's what this path would take us, right? That's one way we could reach the goal, right? Just taking 2 steps at once. Now, if we ended up taking 1 step, then we would be at this position. So from here, we would have that same exact choice, right? We can take 1 step or we can take 2 steps. Now, clearly, if we take 2 steps, we've gone too far, right? We were only trying to climb 2 steps total, but if we, end up over here, then, that's not going to count as a path, right? So that would not count. But as you can see, if we took 1 step initially, then we could take another single step, and that would be another way. So either this is one way we could reach 2 steps, or we could just take a single double step, right? So clearly there are 2 different ways we could climb the staircase, and that's also the result of this problem, and they basically explain it over here. So let's look at the second example, which is basically if we were climbing 3 steps instead of 2, right? So let's look at the drawing. So once again, we're going to do the exact same thing that we did, right? From here, we could take 1 step, or we could take 2 steps, right? And so far we'd get here, but remember our goal is to climb 3 steps, so let's continue. So from here we could take 1 step, which would land us at the result, or we could take 2 steps, which would get us out of bounds, right? That's not what we want to do. So far we have found one way to get us to the result, but let's continue that from over here. Again, we can take a single step, which would get us over here, or we can take 2 steps, which would get us at the result. So now we found 2 different ways we can get to the last step. And lastly, we still have a path to continue, right? We got here by taking 1 step and then taking another single step. So here we have 2 choices: take 1 step, get to the result, or take 2 steps and get out of bounds. So in the end, we see that there were 3 different ways we were able to get to this last step. As you can see, this is getting really hard to visualize with a single staircase. A more easy way would be to get a decision tree to visualize. And at every decision, remember, we can take 1 step or we can take 2 steps. So let's try to visualize the problem like that and see if we can notice any patterns. So let's say we're given n equals 5. We're trying to climb 5 steps. So we can consider, just like the previous drawing, that we're starting at step 0 and our goal is to get to step 5. Now remember, at every given point, we have 2 decisions to make. We can climb 1 step or we can climb 2 steps, right? And depending on the decision that we make, each of these is going to lead to a different path we can take to get to the result. And remember, all we're trying to do is count the number of ways we can get to that result. So in this decision tree, we're going to keep making 2 decisions at every step, and at the end, we're going to count how many different ways were we able to get to 5 steps reached. So we can get to step 1 and we can get to step 2. Let's just continue drawing out the decision tree. From here, we can make 2 more decisions. We can take 1 step, which would get us to 2. We can take 2 steps, get us to 3. And similar here, we can take 1 step, get us to 3. 2 steps, get us to 4. From here, we can also take 1 step, get us to 3. 2 steps, get us to 4. 1 step, get us to 4. 2 steps, get us to 5. Now here, we can see that we reached the result, right? N equals 5. So this is our first path that we could reach to get us to the result, right? You can see we took 1 step, then we took 2 steps, then we took another 2 steps. So this is our result. Once we get to it, that's our base case, right? We're going to solve this recursively, right? That's pretty much what we're doing. This decision tree is basically recursion, and this is our base case. We wouldn't want to continue if we got here. So here we would return 1. We found one way to get to the result. But for the remaining paths, let's continue. So here we can take 1 step or 2. That'd get us to 4. This would get us to 5. So you can see, once again, we found another way we can get to the result. So far we have 2 different paths that can lead us to step 5. And here, let's do the same thing. If we take 1 step, we get to 5. That's the result. If we take 2 steps, we get to 6. That means we overshot, right? We went too far. This is another base case. If this number of steps ever exceeds 5, then we're going to return 0, right? We found 0 ways from this path that can reach the result. So now let's continue. Over here, again, we take 1 step or 2. so we'll get to 4 or 5, another path that leads us to the result. And here we can also take 1 step or 2, which would get us 5 or 6. Similarly over here, right, this is another 4, so the exact same thing is going to happen. You start to see we're repeating the exact same problem multiple times. How can we better solve this problem knowing that? So now we have another 4. We're just going to repeat the exact same thing that we just did before, right? Take 1 step or 2. We know we're going to get to a 5, and we know we're going to get to a 6. So you can see every path led to the base case except for this last one. So let's complete this. We can take 1 step, which would get 5, or 2 steps, 6. Okay, so now our entire decision tree is complete. So what's the result going to be? Remember, red means we're going to return 0. Green means we're going to return 1. So let's just count the number of greens. 1, 2, 3, 4, 5, 6, 7, 8. So there were 8 different paths from the beginning that could reach step 5. But remember, since we started here, we were asking how many different ways starting at 0 can we get to 5? And then we got to a subproblem. We got to a subproblem of starting at step 1, how many ways can we reach 5? From this decision tree alone, we see that there's 1, 2, 3, 4, 5 different ways we can reach the result. And down 2, if we're starting at step 2, there's 3 different ways we can reach the result. Now, if you solve the problem like this, basically using recursion, and you could probably do it with depth first search, because this is basically a tree, and what would be the time complexity of that? Well, clearly, you can see that we have 2 decisions each time, so it's going to be 2 to the power of the height of this tree. What's the height going to be? It's going to be roughly n equals 5, right? You can see that this is going to be the longest path, so that's roughly the height. So the overall time complexity is going to be 2 to the power of n. That's not super efficient, but you can see here, we're repeating the same problem multiple times, right? When we get over here, we're asking how many different ways, starting from 2, can we get to 5, right? And down in this decision tree, we found, yes, there were 3 different ways, right? So then when we get over here, why do we have to recompute the exact same thing? Take a look at these 2 purple blocks I just drew. Notice how this decision tree looks the exact same as this one, because in both cases, we're solving the exact same subproblem. And since we're doing it depth first search, this one is going to be solved first, right? So if we solve this entire problem, what we said was, okay, we found out starting at step 2, there were 3 different ways to get to step 5. So when we get here, why don't we just take that result, store it in memory, store it in DP, or basically this is a cache, right? We're storing it in memory, so then when we get here, we can just say we already know the result of this, meaning that we don't need to draw out the entire decision tree. We're just going to skip that altogether. We're not going to draw this, we're not going to draw that, and we're not going to draw any levels of this tree. So as you can see, I'm eliminating all that repeated work by saving that solution. But that's not all. Right, we see over here, we're asking a different subproblem. Starting at step 3, how many different ways can we get to n equals 5? Well, in this case, it was 2 different ways, right? Notice how this decision tree is the exact same over here, because here we're asking that same question. Starting at step 3, what's the number of ways? And since we're doing the step for search, this one is going to end up being computed before this one. So when we get here, we can just say we already know the answer is 2, so we don't need to run through the entire decision tree again. So in this case as well, we can eliminate that repeated work. So I'm just going to cross this entire thing out. And we're not done yet. See over here, we're asking starting at step 4, how many ways can we get to 5? That same problem is over here. Notice how they have the exact same decision tree. This one is going to be computed first because we're doing depth first search. So once again, let's eliminate this repeated work. So now you can see when we do eliminate all that repeated work, this is what our decision tree ends up looking like. And this is roughly O of n. This is linear time solution. Reason being, we're only solving each subproblem once, right? So we know that the first subproblem, the original problem is starting at 0. Then we get a subproblem of 1, 2, 3, 4, all the way to 5, which is our base case, right? So each of these subproblems is just being solved once. N is 5, so overall the time complexity is big O of n. And this is basically the dynamic programming solution where we are caching the result, aka memoization. So we're using memoization. But this problem can actually be solved with a true dynamic programming solution. As you can see, starting at the result, the result of 0 depends on the subproblem, this one, right? And this subproblem depends on another subproblem, which depends on another subproblem, which depends on another subproblem, which depends on our base case. So why don't we start at the bottom, solve the base case, and then work our way up to the original problem at 0, right? Why don't we start at the bottom, work our way up? This is called a bottom-up. This is called a bottom-up dynamic programming approach. So that's what I'm going to show you. We're going to start at the base case and then work our way up. So remember, we're starting at position 0, and our goal is to get to the 5th step, right? Each time we can take 1 step or we can take 2 steps, right? So I'm going to be storing our result in an array called DP. So we're going to have a position in DP all the way from index 0 all the way up to index n, which is going to be our input value, remember? So remember, we're at the base case initially, right? What's the base case going to be? Well, at the last step, if we start here, how many different ways can we land here? Well, that's just going to be 1, right? That's our default value. So now that we solved that, we are able to solve this one, right? Because remember, this problem depends on the subproblem of this. So from here, let's say we're starting here, we can take 1 step, which lands us at the result. We can take 2 steps, which lands us out of bounds, right? So how many different ways from here can we reach the goal? Again, it's going to be 1. And do you notice how this is always going to be the case? Even if we had something like n equals 100, so let's say this was actually 100 and this was 99, this would always be 1, right? This is always going to be 1 because it's at the goal. And starting from here, it's also always going to be 1 because we can take 1 step, which would get us to the result, or we can take 2 steps, which would get us out of bounds. So no matter what the input value n is, this is always going to be the case. It's always going to be 1, 1. Next, we're going to get to the interesting part. So then we want to know, okay, how many different ways from here can we reach 5? Well, this depends on 2 subproblems which come after it, right? So we can take 1 step over here or 2 steps over here, right? So, and then we get to the subproblem, right? So from 4, we don't need to continue to figure out how many different ways from 4 can we get to 5 because we just computed that. That's why we're using dynamic programming. That's why we have this array, because we already computed starting at 4, how many different ways can we reach 5? And we also, starting at 5, how many different ways can we reach 5? That's also 1. So what we're going to do in this value is basically take these next 2 values, add them together, 1 plus 1, and then we're going to get 2 over here. And we're going to do the exact same thing for this position too. So we know here we could take 1 step or 2 steps, right? So what we want to do from here, 3, is find out how many different ways can we reach 5. We just computed that, that's 2. And from 4, we want to know how many different ways can we reach 5. We also already computed that, that's 1. So what we can do is take these 2 values, add them together, and that's going to be what we put here. So starting at 2, we can get to 5 3 different ways. And at this point, I bet you probably get the idea. We're going to do the exact same thing over here. So what value are we going to put over here? Just take these next 2 values, add them together. 3 plus 2 is going to be 5. And remember, this is what we were originally trying to compute. This is going to be the result. It depends on only 2 subproblems, which are listed right after it. 5 plus 3, that's going to be 8. So that's the result. If you're familiar with what the Fibonacci sequence is, the Fibonacci numbers, that's exactly what we're doing right now. We're starting at the base case of 1, 1, adding these 2 values to get the next result. Then we're adding these 2 values to get 3. Then we're adding these 2 values to get 5. Then we're adding these 2 values to get 8. So you may or may not be familiar with it, but that's what we're doing. And you may have also noticed we're using extra memory, right? We're having an entire array size equals n. That's going to be O of n extra memory. But is it actually needed to have an entire array? Notice how each value, such as this one, only depends on the 2 values that come after it. And this one only depended on the 2 values that came after it. So in reality, we don't need to have an entire array. We just need to have 2 different variables. Let's initialize the 2 variables like this. 1 is going to be this position. 2 is going to be this position. Because starting from here, we want to know how many different ways could we reach the result. If we took 1 step, that's why this is called 1. And if we took 2 steps, that's why this is called 2. And we're basically going to be computing this next value, right? And once we compute this next value, we're going to shift our 1 variable over here, and we're going to shift our 2 variable over here, and we're going to keep doing that until we get to the result of 0. And if we initialize 2 initial variables, 1 and 2, as values 1, how many different values do we have to compute that come after it? In this case, you can see we have to compute 4 values, right? So basically, we compute n minus 1 values. We have to loop n minus 1 times, and then when our 1 variable ends up getting in this position, that's what we're going to return as the result. So this was a really long explanation because we did a lot of analysis, but when I actually show you the code, it's going to be really simple using this idea of 2 variables being shifted n minus 1 times. So as I said from the drawing explanation, we're going to have 2 variables, 1 and 2. Both are going to be initialized as 1. And then we're just going to loop through n minus 1 times. So for I in range n minus 1, and we're going to continuously update these 2 variables 1 and 2. So the first thing I'm going to do is update 1. 1 is going to be set to 1 plus 2, right? Because we're just adding the 2 previous values and then getting the new result. So 1 is being updated, and we would also want to shift 2 to whatever the previous value of 1 was. But you can see that we're updating 1 before we actually shift 2. So what we're actually going to do is store 1 in a temporary variable before we actually update it, and then we're going to set 2 to the temporary variable so that we don't end up setting it to 1 plus 2. We just want it to be set to 1, so we're going to set 2 equal to temp. Once this loop goes through n minus 1 times, we're going to end up just returning whatever 1 happens to land on, and that is the entire solution. We went through so much headache just to get to these 5 lines of code. Hey everyone, welcome back, and let's write some more neat code today. Today let's solve minimum cost climbing stairs, and this problem is very similar to another problem that we've solved that's called climbing stairs. And honestly, I think this is probably one of my best videos explaining dynamic programming. I really walk through all the steps from recursion to memoization to dynamic programming, so I will link this video somewhere on the screen or somewhere on the description if you want to take a look. It's very similar to the problem that we're solving right now, which is minimum cost climbing stairs. It's just a slight variation of that other problem. So we're given an integer array called cost, where cost of I is the ith step on the staircase. And if we pay that cost at index I, then we can either climb 1 step or 2 steps from index I. So in this example over here, we're given an array of 10, 15, and 20. What we're told is that if we pay this cost, if we're at this position, right, and we pay the cost of 10 from this position, we can either take 1 step, which will land us in this position, or we can take 2 steps, which will land us in this position, and we only have to pay a cost of 10 to do that. And also, we are told that we can actually either start at index 0 or start at index 1. So we can either start from this position or we can start from this position. And our goal is to reach the top floor of this staircase. So you're probably thinking, okay, let's just start at position index 0, right? Take a jump of 2, which costs 10, right? Because we're taking 2 steps starting from here. So that costs 10. Then we reach this spot and then we're done, right? We've reached the top floor. So therefore the answer is 10, right? Well, not quite, and it's kind of tricky. I think it's really their fault that they worded this problem kind of poorly. In this case, the answer is actually 15. Why is it 15? Well, it's pretty simple. It's because this is the last position in our cost array, but this is not the top floor. The position right after that is considered the top floor, which, yeah, they don't really specify that anywhere in the description, which is kind of dumb, but that's the thing. So the reason why the answer is 15 is because, remember, we can either start at this index or we can start at this index. If we start here, then we can take a jump of 2, which will land us at the top of the staircase. It only costs us 15 to do that. Or we could start at 10, take a jump of 2, and then take a jump of 1, which would cost us 30. Or we could, from 10, jump to 15, and then take a double jump, which would cost us 25, 10 plus 15. So clearly the minimum was when we start at 15 and then just take a jump of 2. So then the result is 15. So then your next idea might be, let's just be greedy, right? Why not always, let's start at one of the positions, either this one or this one, and then always take 2 steps, right? Why exactly would we ever want to take 1 step when we could take 2 steps, right? And it costs us the same amount. Well, there's an answer to that question, and let me show you an example, a counterexample of why sometimes we would want to take 1 step rather than 2. The main reason is because maybe if we take 2 steps, there's a value over here, something like 1,000, right? A really big number, and then we'd have to either take 1 step or 2 step, but either way, we'd have to it would cost us 1,000 if we land here. Or we could take maybe 1 step, and yeah, we'd have to pay 15 and then have to pay a 20, and then we could, though, take 2 steps to maybe a value over here that's really small, like 5, which would skip us a value like over here, which would be 1,000. So you can't really be greedy. And actually, the second example down here is another reason, is another counterexample of why we can't always take 2 steps. So let's really try to understand how we can at least brute force this problem, because we've noticed that from every spot we have 2 decisions, right? Take a jump of 1 or take a jump of 2, and we can't just be greedy and take a 2 jump every single time. So let's try every single possibility. And if you've watched any of my videos, you know that we like to do decision trees when we're brute forcing. So suppose we start here. We start at index 0 and we have, 0, 1, 2